All right, so we're going to talk about the first derivative test today. And so the first derivative test is something you use to locate relative maximum and relative minimum values. We're also going to be finding intervals of increasing and decreasing today. And so this front is like crazy repetitive, so I think I was just hoping that if I said it enough times, it's going to stick forever in your brain. So if it feels repetitive, it is. So we have this function is going to be f of x, and it's continuous on the closed interval from a to b, and differentiable on the open interval from a to b. And so when I'm looking at this section on my paper, it's the black section. Would you say the function is increasing or decreasing or constant there? Right. All right. Would you say the slope or the derivative is positive or negative? Negative. So I'm going to write that as f prime. The derivative of f is going to be less than 0. All right, what about this red section? How would you describe it in words? It's going to be constant. And then what do you think about the slope or the derivative when a function is constant? Absolutely. All right, and then I'm pretty sure you probably could finish this without me. This green section, the function is increasing, which means the derivative or the slope is positive there. Right? So anytime that the first derivative is positive on an interval, that means that the function is increasing. Negative means the function is decreasing, the original function f. And when f prime is 0, it means that f is constant. Now, I have it typed out that it's f. I said the function. Don't do that. If it's a free response question, don't ever say the function, because there's so many functions. There's the derivative function and there's the original function. So just be careful that you always specify if you're talking about f prime, if you're talking about f or whatever. I'm pretty sure I've told you that before, but I just wanted to double check. So simply put, when the first derivative of f is positive, the function f is increasing. When the first derivative of the function f is negative, the function f is decreasing. All right, and then this is a review from things that you probably learned last year and maybe in Algebra 2, but what results when a continuous function changes from decreasing to increasing? So like we're decreasing and then we change to increasing. That's going to be a relative minimum. They're also called local. So local minimum and relative minimum are the exact same thing. All right, then whenever a function changes from increasing to decreasing, that's where you get the relative maximum or local maximum. All right, so because I have changed the order that we're doing these units, you haven't learned about critical numbers before, so that's okay. So a critical number is going to be a value of x bless you, that makes f prime of x either 0 or undefined. So it's values of x that make the derivative, first derivative, either 0 or undefined. And one thing that you need to know about critical numbers is that they are potential. Whoops, let me spell that right. Relative extrema. So to determine if this critical number is actually a relative extrema, or relative extrema, not a relative extrema, then there's different things you can do. Today we're gonna learn the first derivative test, and we'll practice it for a little while, and then we'll learn the second derivative test. So they both test for relative extrema. So we are going to let C be a critical number, and the function is continuous on the open interval containing C. If f is differentiable on the interval except possibly at C, then f of C can be classified as follows. So the reason that it's okay if the function is not differentiable at C, at the critical number, is because you have a situation like this. So if this was what the function looked like, it wouldn't be differentiable there, but you would still have a relative minimum there because you have that sharp turn. So it's okay if at that point the function is not differentiable. So anyway, if f prime of C changes from positive to negative at C, then f has a relative minimum at the point C, f of C. All right, and so that's gonna, I think you probably could figure out what that looks like. So if C is here, you're gonna have a situation like this. It's a critical number because that derivative was 0 there. It's a horizontal tangent line. And then FC is changing from negative to positive. All right. Then if f prime of C changes from positive to negative, then you could guess that f has a relative maximum. At that point. All right, that's going to be a situation like that. We have a critical number because we have that horizontal tangent line, and then that results in a relative maximum. All right, and then there are situations when the derivative is 0, or the derivative is undefined at that point, but it doesn't, the first derivative sign doesn't change. And so if you have a critical number and the derivative is the same on both sides, either positive on both sides or negative on both sides, then f of C is neither a relative maximum nor a relative minimum. And so that is going to look like one of these two. So it could be like increasing and then go flat and have a slope of 0, but then start increasing again. Situation like that, where it never stops increasing. Another situation, and I should have drawn these like this, the critical number happens also when the derivative is undefined. And a time when the derivative is undefined is when there's a vertical tangent line. So it could be something like this, where you're increasing, it goes vertical, and then you start increasing again. And that is not going to be relative extreme. Do you guys remember what that's called? We learned it a little bit in pre-calculus.
Like what's called?
Like what's happening right here and right here.
Oh.
Yes, good job. Point of inflection. The concavity is changing. All right. We'll get into that later. All right, so these are the things we're going to do. We are going to first find the critical numbers, if there are any, And to do that, I'm just going to write a little hint. To do that, we need to find the derivative. Thing we do every day in calculus so far. And set it equal to 0 or find where f prime of x is undefined. That will always give you the critical numbers. All right. Then we're going to find the intervals on which the function is increasing and decreasing. To do that, we're gonna do a number line. You'll be able to see it, and then we're going to test the derivatives on each side of the critical numbers. And then C, we're going to apply the first derivative test to identify any relative extrema. All right, so let's look at example 1. I'm going to start with going ahead and finding this derivative. Now, this is a polynomial function. The original function was polynomial. The derivative is also a polynomial, but it's a polynomial function is never going to have a place where the derivative is undefined, but we should have at least one, maybe two values in this case where the derivative is 0. So we'll set it equal to 0 and then just use some algebra to find our critical numbers of 0 and 2. All right, now I'm going to go back up and just make a note that this is continuous everywhere. That matters as we're doing these problems. Because it's polynomial functions, they're continuous and differentiable everywhere. All right, and then for B, we're going to do a number line. If there had been a value where this function is not continuous, we would have to label that on the number line so we would know that you can't have a relative maximum, relative minimum where a function is undefined. So in this case, we don't have to worry about that. So we'll just put in our two critical numbers. And then what we want to know is if in between those critical numbers, if the derivative is positive or negative. And so we are going to test a point in each region, and we are testing it with the derivative. Because B is we're just determining the intervals of increasing and decreasing. All right, so you can pick any number in those intervals. So I'm going to put in -1, 1, and 3 into the first derivative. All right, and I would try to do as much of this as possible without a calculator. If this was a calculator question, it would be really easy. I don't need to rewrite that. It would be really easy to find intervals of increasing and decreasing and relative max and min with a calculator. So this is not something that you would be doing with a calculator. All right, and I don't actually have to find the number. I mean, it's easy, it's 9, but what I need is to know if it's positive or negative. Here. All right, and then we'll just do the same thing for 1. 1's easy. We just add or subtract the coefficients, and I know that's going to be a negative. 3 might take a minute. And again, I don't have to know the exact value. I just need to know positive or negative. Now, one thing I've seen my students do over the years, which I think is really smart, is they'll label these. So like with arrows. So if we're doing the first derivative, whenever it's a plus for the first derivative positive, we know we're increasing. And so they would just draw a little section of the graph that's increasing. And then negative means decreasing. And that helps two things. It helps you to answer the first part, and then it's going to help you to do part C also. Okay, and so to answer this question, we would say f of x is increasing. Now this is where things might get a little confusing for you. From what you learned maybe in Algebra 2, if these critical numbers, if the function is continuous there, we include them in these intervals. You're not going to ever include infinity, obviously, or negative infinity. And if the function is undefined, you don't include it. But we do include 0 in our increasing interval. So it's going to be from negative infinity to 0. All right, and then we're going to pick up at 2 to infinity. And then in between those is 0 to 2, the function is decreasing. Now it feels like at that point the function is not doing either, but a function can't be increasing or decreasing at a point. A function increases or decreases at an interval. So that's why you always include it if the function is continuous. I know, I wish I could go back and teach Algebra 2 differently when I taught Algebra 2, or just talk to the Algebra 2 teachers, but I don't think it matters. So just include it unless the function is not continuous there. All right, and then let's talk about the last part. This should be pretty easy considering that we drew those arrows and it's kind of obvious where there would be a relative maximum. Now we are going to give these as ordered pairs, so that's going to take a second, but the x where there's a relative maximum is 0. And then if I want to find the y-coordinate, we go back to the original function and we're going to put 0 in for x, and that's going to be 4. And then we can tell that because when x is 2, f, or the first derivative changes from negative to positive, which makes it have a relative minimum. So this is going to be 8 minus 12 plus 4, which ends up being 0. All right, if this was a free response question and you needed to justify, you justify using the first derivative. So if we're justifying the reason why this is a relative max, you would say f prime changes from positive to negative when x is 0. Okay, so let's do one that's not a polynomial. So polynomial derivatives are crazy easy to do, but obviously there's other functions out there. This one's my favorite function. Is this function continuous everywhere? Do you guys remember what it looks like? It's the bird in the sky. This one is continuous. Okay, so we are going to start off with finding the critical numbers by finding the derivative. we technically would need to do the chain rule here, but what is the derivative of the inside? It's just 1. So you can write that 1 if you want, or just do it in your head. It doesn't matter. All right, so whenever you have a rational function and you're trying to find where it's 0, you just look to see where the numerator, what makes the numerator 0. Would anything make this numerator 0? No. Okay, and then when we want to find where the function, a rational function is undefined, is what would make the denominator 0. So what would make this function undefined? Not 0. Yes. So that means that there's a critical number there. And if you could visualize what this looked like, you already knew that that was going to be a critical number, because you know that's where the little sharp turn is and the bird flying. All right, and then for B, we're going to do our little number line. We label our critical number on our number line. Right, and then we just need to test each region. All right, is this going to be positive or negative? And then I know that when the first derivative is negative, the function is decreasing. And when the first derivative is positive, the function is increasing. I should say f, not the function, sorry. So f of x is increasing from -2 to infinity. Struggling on my infinity there. All right, so what am I going to have at -2? Relative minimum, good. Okay, and then we would want to go back to the original function and plug in -2. Oh, that's nice. And that's just going to be 0. I know. If it ever doesn't, do you guys know what to do if you need to raise something to the 2/3?
Is that where you take the
Cube root and square it. Good. You can square in any order. So you could do cube root and then square, or you could do square and then cube root. It works out. Okay, one more to do. Okay, we're good. Is this function continuous everywhere? No. Where is this function undefined? 0. All right, that's going to come into play whenever we're doing our number line. All right, so part A, we are going to find this derivative. To find the derivative, I am going to rewrite it as x to the -1. Then I want to find the critical numbers, which are going to be where the function is zero, where the derivative is zero and where the derivative is undefined. So let's start with zero. Okay, so I'm just going to move over my x, 1 over x squared, and then multiply to solve. Are those my only critical numbers? 1/2 and negative 1/2? No, because there is another place where this function is undefined. So another critical number is going to be, x equals 0. Okay, so here we go. Let's do our number line. And then I always, if there's a place where the function is not continuous, I make a note of that. I'm just going to say not defined. So we can't say that there is a relative max or min at 0 or a point of inflection or anything. That point doesn't exist in our function. So just write myself a note to remember that, because sometimes I get caught up. And also when I'm doing my intervals of increasing and decreasing, I can't include 0 because it doesn't exist there. The function doesn't exist there. Okay, so let's do f prime of -1. Ooh, we need to find something between -1/2 and 0, so I'm going to say -1/4. We'll do +1/4 and 1. All right, so we're putting them into the first derivative. And I just need to know positive or negative. So when I square that negative, I'm going to get a positive. So 4 minus 1 is definitely a positive. This one I might need to do a little bit more to figure it out. So when I square -1/4, I'm going to get positive 1/16. And then to divide by that, I basically just do the reciprocal. So that's a negative in that section. So what's going to happen when I put in positive 1/4? Is it going to be the exact same? Yeah. And then when I put in positive 1, it's going to be the exact same as when I put in -1. Okay. And then I'm going to just draw my little arrows. Okay, so when I'm doing my intervals of increasing, I do include -1/2 and 1/2. However, I cannot include 0. And this is kind of weird. If it did include 0, I could say from negative 1/2 to positive 1/2, the function is decreasing. F is, but there's nothing at 0, so I need to be careful that I don't include 0. Okay, and then I need my relative extrema. And just to save time, I'm just going to tell you, you go ahead and you get -4 when you plug in 1/2. We could go through the process if you wanted to. And then positive 1/2 is going to be 4. Now this always messes with people's heads, because the relative max is higher than the relative minimum. And that happens. It is this function is a rational function, but what happens is the relative max just means it's higher than the points around it. It's not the highest.
Wait, which one's the max again? The lighter blue or the darker blue?
Oh, I wrote max twice. Sorry.
Oh, it's up.
This one is the min. And so what's happening is somewhere on the graph at -1/2, -4, you have like a little that, and then at 1/2 +4, you have that. So it's okay. It happens. It feels like it's wrong, but it's right. A min can be higher than a max.